We're now ready to take on E equals mc squared. Let me just quickly remind you of the meaning of E equals mc squared. The idea is we want to establish that energy and mass are convertible. They can be transformed one into the other, and that c squared is nothing but the conversion factor that takes you from mass to energy. Now, we actually have already seen a hint of E equals mc squared in our formula for the kinetic energy of a particle. And let me just show you this little hint. It's just suggestive, but then we will do the real thing in a moment. The hint that I have in mind is when we talk about the energy of an object, we know that we usually break that up into kinetic energy plus potential energy, which means that kinetic energy can be written as the total energy minus the potential energy. So let's take the form for the kinetic energy that we have and write it in this way. So kinetic energy we have as m naught c squared times 1 over the square root of 1 minus v squared over c squared minus 1. Let's write that in a form that's similar to what I have on the top line as, say, m naught c squared times gamma, so that's just my gamma over there, minus m naught c squared. And this way of writing it is suggestive. In fact, it's true. But this might lead you to think that the energy, total energy, is given by m naught c squared times gamma, and that there's some kind of potential energy, stored energy, if you will, in the mass of a particle itself, and the amount of stored energy looks like m naught c squared. So again, that's just suggestive. Let's now undertake a real physical mathematical argument to derive E equals mc squared. And to do that, I am going to play a game that is very similar to the game that we played in trying to come up with the relativistic equation for momentum, right? Remember how we did that? We looked at one and the same collision, but we looked at it from two different frames of reference. We are going to do the same thing now with another specially chosen collision between two particles. And the kind of collision that I have in mind that I'll show you here involves two particles coming together, slamming together, and sticking, creating one particle whose mass is going to be bigger than the mass of the particles that come in. Now, the thing that I want you to think about, as this will be critical to the approach that we're taking, ordinarily, if particles slam together, we assume that we hear something, we assume that the air molecules get jostled, and therefore some of the kinetic energy that comes in gets converted to waste, heat in the environment. But we are going to imagine that in this kind of a collision, there is no environment to take away any energy. We are going to assume that all of the energy is totally in the system at the end if it was there in the beginning. And the question is, therefore, where does the kinetic energy of the incoming particles go? And we are going to argue that the kinetic energy that they slam together with goes into increasing the mass of the particle that they create. Their kinetic energy is going to be transmuted into an additional mass of this particle that they create. And we're going to calculate how much additional mass this particle gets from the kinetic energy, and that will lead us to the promised land of E equals mc squared. Now, to do that, I'm going to consider that collision, but from another frame of reference. So this frame of reference, as you will see, is one in which the second particle, remember there's one particle that came in from here, the other particle came in from the other side. Let's look at a frame of reference where that second particle is at rest. In other words, we have a frame of reference that is moving to the left with the speed of the original incoming particle from the right. So here it is. One particle is at rest, the other particle slams into it, and of course, finally, it pushes the combined particle off to the right. Now we're going to do a mathematical analysis of this collision in particular and show that the kinetic energy must be transmuted into mass. So I'll call this particle over here particle A, and it may be a different color from what you just saw a moment ago, but don't worry about that. This guy, particle B, is the one that it slams into. Let me get that in a closer line over here. I don't know if that's much better, but imagine these guys are in the same line. So this guy over here on the left is coming in. He slams into that particle. So this is what happens, say, before the collision. And then after the collision, they join together into the third particle, which itself is kicked off to the right because of the incoming collision from the left. So, if you will, this is what we had before. This is what we have after. And let's now fill in some of the mathematical details and do some calculation. All right, so let's call this guy A. Let's call this guy B. You might think I'd call this guy C, but I won't because I don't want to get confused with the speed of light. So let me call it particle D. And I am going to assume that in the laboratory frame that both of the particles that we looked at over here, assume that these guys were coming in. So I might as well just have the lab data as well over here. So in the laboratory frame, what was happening is the particles were both coming in. So one particle was coming in this way. The other particle was coming in this way. And from the laboratory perspective, this guy, say, had velocity v. This guy has the same speed v in the opposite direction. So this is particle A in the lab, and this is particle B. And this is particle D. So if that is the picture from the lab point of view, then from the moving frame, which makes particle B stationary, there is a standard calculation that we are now quite familiar with to determine the velocity v prime of A in the moving frame. All right? How do we do that? Well, we know that the frame that we are looking at, the frame in which B is at rest, is a frame that's moving this way with a velocity equal to B, which means that v prime gets increased by the amount of the velocity of that frame. It's got velocity minus v, because that frame is moving to the left, but we know there's a correction factor, and the correction factor is 1 plus v times v, v squared over c squared, just our favorite velocity combination formula. Good. So that's the velocity of particle A in this frame of reference. What about the velocity of particle D? Well, in this frame, particle D was at rest. So if the new frame is moving this way, then particle D is moving that way with velocity v, as I've indicated over here. Now we're in good shape because we can calculate the consequence of momentum conservation in this frame of reference. So let's write down that the momentum of particle A in this new frame of reference is equal to then the mass of particle A times its velocity times gamma. So we have to divide through by square root of 1 minus v prime squared over c squared. And therefore, we can substitute in this expression for v prime in terms of v. So we've got 2v over 1 plus v squared over c squared. We can plug that expression for v prime into here. And I'm going to leave it to you to do the algebraic simplifications, couple lines of algebra, not hard. You'll find that the momentum of particle A in terms of v is 2m naught v divided by 1 minus v squared over c squared. OK, that's the momentum of particle A. What about the momentum of particle D? Well, first off, this, of course, is equal to the momentum of particle A by momentum conservation. But let's write down the formula for the momentum of particle D in its own right, which is equal to its rest mass, m naught of D, times its speed v times gamma, which is square root 1 minus v squared over c squared. And the nice thing now about equating that expression to the momentum of particle A is that we have the ability to solve now for the rest mass of particle D in terms of the rest mass m0 of particle A. And equating those two expressions, we'll find that m0 of D is 2m0. Now that's not quite the end of the story, because if you look over here, I've got a 1 minus v squared over c squared in the denominator for the momentum of particle A. But for D, I've got a square root of 1 minus v squared over c squared, which means for these guys to be equal to each other, I need to throw in one more factor of the square root of 1 minus v squared over c squared. And that is a remarkable formula if you think about it for a moment, because it's basically telling us that the rest mass of particle D, that's this guy that we have over here, the mass of particle D when at rest is not equal to 2m0. It's not equal to the sum of the masses of the two particles that are coming in. It's a little bit bigger than the sum of the masses of the two particles coming in. This expression right here is showing us that the kinetic energy of A and B as they collide with one another is being transmuted into an additional amount of rest mass of particle D. You would have thought that the rest mass of particle D, you just add up the mass of A and the mass of B to get 2m0. But we don't have 2m0. We have something bigger by the factor gamma. So let's actually calculate how much bigger it is than we would have anticipated. So let's look at that expression that I have over there, which is 2m0 multiplied by gamma minus 2m0. This is what we would have expected. So the difference then is equal to, let me call this delta m of D, is equal to 2m0 times gamma minus 1. This is the additional mass that this particle gets from a conversion of the kinetic energy between those two incoming particles. Now, how much kinetic energy did we have at the start? So from the laboratory expression, at the start of this experiment, when A and B are coming in, each of them has the same kinetic energy. So kinetic energy total is equal to 2 times the kinetic energy of each of them individually, and that is equal to m0 c squared times gamma minus 1. That is the formula that we have already derived. So now you see what's going on here. The kinetic energy equal to 2m0 c squared gamma minus 1 is being converted, this is being converted into that amount of rest mass. So if I think about that in equations, I'm saying that the change in the mass of this particle D can be thought of as equal to the change in the kinetic energy. This is the kinetic energy at the start. At the end, there's no kinetic energy, so that's the change from before to after. You take the change in the kinetic energy, divide through by c squared in order to get the amount of mass that that turns into. And that is a nice expression, because if you think about it, the additional mass from the colliding particles is just mass. It's like any other mass, and we're basically saying that the particle D at rest has some frozen energy inside of it. It's holding on to the energy that was initially kinetic energy. Now it's turned into mass, and you could in fact envision building up the particle D by many of these collisions over and over and over again, making its mass bigger and bigger until we have the form that we have here. So what this is really telling us is that there is a rest energy, which is what we usually call it, a rest energy of the particle d, an energy that it embodies even when it's sitting still, because that kinetic energy has been turned into that, which is given by the mass of d at rest multiplied by c squared. So that kinetic energy turns into mass times c squared. The particle is at rest, and yet it embodies that amount of energy. Now, if the particle is moving, then it has its own kinetic energy. So let's get the total energy of this particle, which we would get by looking at the rest mass times c squared times gamma minus 1, the formula that we derived earlier for the kinetic energy of a particle. But now we add in this additional energy that we have just established that it contains even when it is sitting still. And putting those together, we get at our formula m0, so the mass of this particle when it's at rest, times c squared times gamma. And that is Einstein's famous formula. That is E equals mc squared, because typical notation that we use, if we define the, in fact, let me just do it over here because it's our final and important equation. So if we define the mass as we have been doing, now we have established it mathematically, m of v defined to be the rest mass of an object divided by 1 over the square root of 1 minus v squared over c squared, then the equation I have on the other board is nothing but E equals mc squared with this definition of the relativistic mass. So there you have it. E equals mc squared. It simply comes from this beautiful little argument. The kinetic energy of the incoming particles slam together, and we can show that it increases the mass of the particle they create to be larger than just the sum of the masses of the incoming particles. Their kinetic energy is transmuted into mass. The particle at rest therefore has that energy inside it, and the amount of that energy is given by this formula. Delta m is the change in the kinetic energy over c squared, which gives us E equals mc squared, with the mass being the mass that depends on v. Mass goes like m0, 1 over square root of 1 minus v squared over c squared. One quick little example so we can see the power of this result. We've shown here that energy is being turned into mass. Of course, you can go the other direction too. Mass can be turned into energy. And doing a little calculation just to see the power of this result, if you had 10 kilograms of potatoes just sitting at rest, plug that into E equals mc squared to get the total amount of energy that the potatoes at rest would give you. Gamma in that case is 1, so it's just m0 c squared. Plugging that in, you find that the result is 9 times 10 to the 17 joules, which in kilowatt hours is about 10 to the 11 kilowatt hours. Just to give you a feel, New York City uses about 10 to the 11 kilowatt hours each year. So were you able to extract all the energy in 10 kilos of potatoes, you'd be able to power New York for a year. That really gives you a sense of the wonder and power of this unexpected interchangeability of mass and energy in Einstein's famous E equals mc squared.